Again, good morning and welcome to basically the last part of chapter 20. And today we're going to finish chapter 20. We'll also have lab this afternoon. I'm going to change the due date for this lab because of the fact that we have two things coming. First of all, we have the spring break next week. And then also, I want you to spend a good amount of your time, basically, at least during this week and also next week and the week after, preparing for the actual midterm, which is going to be the week immediately after the midterm, after the spring break, I'm sorry. Okay, so that is one change that we're going to make in terms of the due date for the lab, and also in terms of the due date for the discussion, because it involves you guys working on the solving these problems. So we're extending the due date for the lab, for the discussion, and to allow you to focus more on the review for the exam. And honestly, and this is upfront, and I'm going to mention it again this afternoon and probably next time when we meet, the actual lab that we're going to be doing this afternoon is actually also preparation for the exam. In other words, there will be 8 engines in this lab, where you're supposed to calculate, to pick up 2 of them, not all 8 of them, and to calculate everything that you have to calculate on those engines, including at some point, you're going to be calculating the entropy of those cycles involved with those engines. So in other words, the lab is actually an essential part of preparation for the actual midterm, which is coming soon, immediately after the spring break. So the due date is going to be postponed, okay, to allow you to prepare and focus on the preparation for the midterm. But that does not mean that you should ignore this lab, because of the fact it's going to help you actually prepare. So the only thing that you're not basically going to be doing is actually composing the lab report and submitting it, but I'm hoping that you complete all the activities related to it prior to the actual midterm, okay? Does this make sense to you guys? At least I know probably we still have to go through it to make more sense, but hopefully you understand the idea that although these assignments are going to be postponed, but you still have to do them before the due date. Good. When I say that you have 8 engines, you're going to be required only to do 2 of them, a part of your lab report. You really have to look at every single one of those engines and the different processes. These are theoretical engines that you're going to have in the lab, in a sense, unlike the engine that we have before us, which is really a practical engine, because that's the auto engine that we started last time, and that is used in vehicles. And I was tempted to do actually the diesel engine, but because it involves another parameter in it that makes a little bit the calculation lengthy, I refrained from it. But I think it's one of the problems that we can do in the discussions also. It and also the Stirling engine. Those are 4 cycle, basically 4 processes cycles, whereas the problems from the lab, they're all actually theoretical 3 process engines, basically cycles, okay? So that is one change. We have lab this afternoon, and we have class this coming Wednesday. And please reach out if you need help with any of your lab assignments or your other assignments, or you don't understand something and things like that. Maybe, depending on how it goes today and also this afternoon, maybe we will start optics today. If not, we're going to defer it to after the midterm, okay? We still have, after chapter 20, 4 more chapters dealing with optics. And optics is divided into 2 kinds of optics. There is geometrical optics and also wave optics. Okay, so we're going to do both of them. Okay, 2 chapters each. So let me share the screen and see where we stopped last time around. So last time we were describing the auto cycle, part of the auto engine. And we said that it doesn't matter where we start. The key thing in here is we're going from a point, and I'm following the convention of the book, okay, in terms of this engine. The ratio, which is called the compression rate, and here they use the symbol R for it. If you see the symbol rho for it, don't be too alarmed. That is also the same thing. It's the ratio of the biggest volume when the piston is fully extended, okay, versus when it's compressed the most. So the piston in a given chamber goes like this. So you have the intake of the fuel, and then it's going to expand up to a certain volume. So this is V2. This whole thing now is V2. Then it's going to compress. So this is the motion of the piston, okay? When the two valves basically are, when this valve is open for the intake, or even when this one is going to be open and this one is closed, and when during the exhaustion of the exhaust cycle of the exhaust stage of this engine. So when the volume is fully expanded, this is basically what V2 is. When it's fully compressed, this is the volume, V1, okay? The ratio of V2 over V1 is what we call the compression rate. Every given engine has this motion in here for when the piston goes all the way fully extended to when it's completely compressed, okay? And it goes up and down basically during an intake stage and also in expulsion stage or exhaust stage. It gets rid of the mixture, the byproducts of the combustion, which usually are water and carbon monoxide, and they go through the exhaust system, and then it takes more of the air fuel mixture, okay? And then it goes through a whole cycle again. So this is basically what the whole thing is. So depending on where we're starting. So we're starting in here during this stage A, okay? We're compressing it, getting rid of this basically gas in here during the exhaust stage. Now we're back to V1. At that point, heat is taken through through the chemical reaction, and that is basically where the spark plug goes on, okay? When the spark plug goes on, in this case, the mixture goes through a chemical reaction and generates a lot of heat. That is the heat that is taken during this stage, okay? So this is the QH coming from the chemical reaction. And then, so it's going to happen at constant volume. It's going to happen at V1. Then it's going to expand, okay? Because once, of course, this is closed during the combustion, when it's going to expand during that stage in here is when the gas is going to basically go through to V2. In this case, it's constant heat. There is no heat taken anymore because the chemical reaction is stopped at that point. Okay, that is when it's going to basically move the, usually there is something attached to it in here that turns the flywheel and turns all of the engine machinery. So it's going to be doing work during this stage, okay? And at that point, the temperature, of course, drops. And then the gas is compressed actually by the motion of the flywheel itself. It's going to push it back so that the pressure now drops back to, to where it was before, okay? And the whole cycle repeats again. Compression, I'm sorry, this is where it's going, the gas is going to be released in this case, okay? And then we're going to start again, the whole cycle again, okay? So this too, when it releases the gas in here, this is when it gets rid of that excess heat that it has in here that did not fully get rid of it up to point D. And then finally is going to get rid of that, and then the whole process is repeated again, okay? Because during this stage, it's going to be taking gas, compressing, and so on and so forth. So this is a cycle of the auto engine. There are two parts of it, two legs of it that are not shown, okay? And that is the actual intake of the fluid, fuel and air mixture, and also the actual expulsion of the of those byproducts of the chemical reaction, okay? So those two, it's actually a 6-stroke engine, but it is not shown in here that it is basically a 6-process engine, but it is not shown in here the other two because they are irrelevant in terms of the calculations for the energy and the efficiency of this engine. Okay, the work in here is going to be this area, and you have to be very, very careful with the way that this thing is laid out. I'm going from point A to point B to point C to point D back to A again. Clearly, I'm going on a clockwise motion. So because I'm going to clockwise motion, the work naturally has to be negative, okay? The convention of the book has it backward. So the standard convention is W net in this case is negative because you're going clockwise. However, the book in here takes it in absolute value, basically takes the definition of work as the positive, the integral of PDV, okay? Which will turn out to be positive in this case, stating that it is doing work, okay? That's basically what it is. So if you take it this way, the work is going to be just the difference between the Q hot and the QC. The reason why I'm adding them is because QC I know is negative. Q hot is going to be positive. So this is the net difference between them. So you can write it alternatively as the absolute value of Q hot minus the absolute value of QC. It's the same thing because QC actually is negative. Okay, and that is fine. That is fine. So you write it either way, but be mindful of your signs all the time, okay? The standard books everywhere, and this is actually what I do actually too, is W naught is not defined, W is not defined as such, but it is actually as, where is my mouse? Where is my, okay, let me move down in here because I lost the, W the way I define it is minus PDV. That's not me actually, it's defined everywhere, okay? So in this case, is W, if dV is positive, this work is negative. That means that the gas is expanding, okay? dV is positive. That means the gas is becoming bigger and bigger. So it's doing work against its environment. In a sense, it's losing energy from its internal, because somebody has to pay for that expansion. And that is the gas itself. So it has to lose energy in the form of work. So that is the standard definition, but the way that this book uses it and the way that we're going to do it also in the lab is we're going to follow this weird convention. However, in your mind, you have to be clear of what's going on. In this case, the cycle is going clockwise. This is how the clock goes. So this is an engine. If you take this engine and you put it outside, for example, of your house, and reverse the process, basically go through this process, extracting heat from your house, and compressing, and the engine goes to the compression station here for the adiabatic one with no heat exchange, and then dumping that heat outside. So this arrow will be backward. And then again, it goes through its closed cycle. That is going to work as an AC unit. So you can take that engine from your car and convert it and have basically switch the pipes, okay? And have it work as a pumping heat from your house. In that case, if it is going counterclockwise, it's actually a heat pump, like an AC unit or refrigerator, okay? So you can take the same engine and do it the same thing. In this case, the only reason why I know it's actually a, is this clockwise? No, this is counterclockwise. So this is why it's a heat engine, okay? So you have to be careful with these things in here. Anyway, so we're going to find the efficiency of this engine. So the efficiency is clearly, again, the efficiency, sometimes we use epsilon for it, okay? E is just the network over the amount that you really have to pay for it, okay? The work that is delivered. So this is why, if you put it in absolute values this way, you're actually in a safe house. Because if you define W as just take its positive out, because that's an engine, you want something out of it, okay? And the thing that you want out of it is this area, which is the work, okay? And divide that by QH. It's going to be negative if we follow the standard convention, because energy is lost from the engine somehow. Where is that energy coming from? It's coming from the spark plug, basically. Not spark plug itself, I mean from the chemical reaction in here that spark plug has triggered, okay? Basically the fuel itself combining with the air, that is what that energy is coming from. So as far as the car is, itself is coming from this gas, the mixture in here, okay? So that's why technically it has to be negative, but if you follow the convention of the book, it's going to be positive. So we're going to follow that. It doesn't matter. So we're going to take its absolute value. And its absolute value is going to be QH minus QC divided by QH. Again, QH is what costs you in this case. What is really what needs to be done in this case, the cost in this case. Okay. Obviously, this expression is going to be equal to 1 minus QC over QH, okay? Or 1 plus, because I know QC is negative and I know QH is positive, so I can write it in terms this way. So because QC is actually, as I was talking about, the fact that this is actually negative, so I could write it as QH plus QC, and QC in this case is going to be, as the arrow indicates in here, is going to be a negative number because that's energy dumped to the external in here. This is the exhaust that goes and cool the engine down, okay? And because it's working as an engine in this direction, okay? So now we have QH taken, do this. There is no Q in this cases because it's an adiabatic process. From A to B and from C to D, it's adiabatic. So there is no heat exchange during that time. There is only work, okay? So let's find this QC and QC. QC and QH, both of them are constant volume. Both of them happen at the same volume. So QC is going to be NCV because heat at constant volume, you have to use the specific heat, times the final temperature, which is TA minus TD. If you look at it clearly in here, there is a temperature in this point in here, which is the temperature at point A, and this is the temperature at point D, okay? TA is below TD, therefore this number is actually negative, as I was saying before, that this number must be negative, because the point TA falls below TD. TA is below TD. So therefore, this number is actually negative as expected. So we're getting rid of heat in here, in this form in here, from a higher temperature to a lower temperature. And that's exactly what this point is. If you look at the PV diagram, all of the lines that are above, they are higher temperatures than the lines below. Same thing, the temperature at B is less than the temperature at C. But in this case, it's a heating. We're going from a lower temperature TB, because we're going in this way, to a temperature TC. So the temperature TC in this case is higher than the temperature TB. So how are we getting that heat? Because there is no expansion in here. This is constant volume. We're getting it from the hot source, from the chemical reaction that happened in here. So in this case, QH, it's the same thing. QH is going to be NCV, the final temperature, which is TC, minus the initial temperature, which is TB. We're looking at this stage of the cycle. TC is the final and TB is the initial. So all I have to do is take this ratios. When I do the ratios, the NCV is canceled. So it doesn't matter what the molar specific heat for this gas is, okay? Which is mainly air, by the way, which is the specific heat is that of the air for the most part. It doesn't matter with the number of moles either. So this efficiency is going to be independent of both of them. So it's going to be E equals to 1 plus NCV cancels. So I left with the TC, which is TA minus TD. TA minus TD divided by TC minus TB. Obviously, this is positive because from the diagram, TC is higher than TB. TC is higher than TB. But TA minus TD is negative. So this is actually a negative number. We need to find the relationship actually in here between these temperatures because, let me use a different pen. Do I have a different pen I didn't use? Let's use the green. In this point A and this point B are part of the same adiabat. So the relationship between the pressure at point A and the volume at point A and the pressure at point B and the pressure at point B are related. Pressure at point A times volume at point A to the power gamma is the pressure at point B times volume at point B to the power gamma, because part of the same adiabat. In the TV diagram, T temperature at point A times the volume at point A to the power gamma minus 1 is equal to T at point B times V at the point B to the power gamma minus 1, because both of them are part of the same adiabat. As a matter of fact, I'm going to use this relationship in the TV diagram instead. So what I have then is T at point A times the volume at point A to the power gamma minus 1 is equal to, because it's an adiabatic process, that's why I can do that, times TB times VB to the power gamma minus 1, which means that I can express TA in terms of TB. So let's find what that turn out to be. TA is equal to TB times the ratio of the volume at point B divided by the volume at point A to the power gamma minus 1. But volume at point B and volume at the point A are related. The ratio of volume V2 over V1, which is volume of point A over volume of point B, is exactly R or rho, depending on which convention you're going to be using, okay? The compression rate, that's all. How much did the piston go from this volume to this volume? That's all. So that is exactly what that is. So the volume of point B is when it's compressed. The volume of point B when it's completely basically open. So in this case, it's actually 1 over R to the power gamma minus 1. So it's TB 1 over R to the power gamma minus 1, okay? So we know one condition here. So we know how to express this one in terms of that one. How about TD and TC? Let's look at them. I'm going to use a different color, red now. TD, the point D, and the point C are also part of the same adiabat, different adiabat. But nonetheless, the pressure in point B, D, and the volume in point D to the power gamma are related to the pressure in point C, which is PC, and the volume, which is V1 actually, to the power gamma, okay? But I need actually the temperatures. This is how the temperature look like. I have TD times the volume, which is VD now, to the power gamma minus 1, is equal to, again, the point C, which is TC times VC to the power gamma minus 1. So I'm going to use that expression in here. And I know that VD is actually V2. And VC is actually V1. So the ratio is actually also gamma. That is the compression rate, because this is happening an isochoric process at the same volume. And this is also the same volume. So these two volumes are actually V1 and V2, and the ratio is exactly R2. So the point, again, let me use a regular pen. So we have TD VD to the power gamma minus 1 is equal to TC VC to the power gamma minus 1. Again, this gives me TD is equal to TC times VC over VD to the power gamma minus 1. And again, VC is exactly that volume V1, and VD is R times V1. Okay, again, VD is V2, and VC is exactly V1. So the ratio I have actually VC over VD is actually 1 over R to the power gamma minus 1. So that too gives me the same stuff. It's TC times 1 over R to the power gamma minus 1. Okay. It seems like TA is related to TB from this expression. TA and TB are equal to this one. TD is related to TC through the same relationship, through the same factor. So all I have to do is now sub the value for the efficiency of this engine is going to be 1 plus. The same factor is 1 over R to the power gamma in the numerator, because I have found TD and TA. Both of them have the same factor of 1 over. So this is equation 2 if you're keeping track. So we're going to take 1 over R to the power gamma minus 1 times the numerator. Now I'm left with, for TA, I have TB divided by this quantity, and for TD, I have TC divided by that same quantity, divided by the denominator, and the denominator TC minus TB. This quantity is the same as this quantity, except that I need to flip the sign, that's all. It's a -1. So the efficiency now for this Otto cycle is just related to the compression rate. Okay? We're going to do a problem for E7 that's going to go in detail about the VW engine, actually. And in the VW engine, we're going to basically look at all of these numbers in here. They give you R, they give you all kinds of things again. This very same calculation is repeated again in the lab. So if you have had a chance to go through it, that's actually the same calculation that arrives at the efficiency for an Otto cycle, Otto engine. If you're going to be doing the diesel engine is a little bit different than this one. The diesel engine has actually an isochoric process and also has an adiabat in here. But at this point in here, it does not have really an adiabat, an isochoric process. It has an isobaric process. So it's slightly different. So you have an A, B, C, and D. So you need the compression rate now too. So you need the ratio of these two volumes. So this is still R, but you need this quantity. Sometimes this R is used as rho, the ratio of this is the compression rate. And you need this ratio also of VC, which is the intermediary volume with the fully compressed cylinder. And that ratio is called actually beta. Sometimes it's referred to as alpha. It doesn't matter the symbols, but this is called actually the cutoff ratio. Ratio, not ration. Okay, and that is a compression ratio. So this would be your diesel engine. Again, it's due to Mr. Diesel who did that. So again, this is actually different one. The advantage of the diesel engine is that you can have a huge, basically, compression rate because of this process in here. So you can have a lot better R in this case, which makes the efficiency much, much better than that of an Otto engine. Obviously, there is another twist to the expression. The efficiency is not exactly dependent only on R. It depends also on this factor beta, the cutoff ratio. And there is a value with which actually the Otto engine will be better. But then usually you can tweak that so that it's still the diesel engine will be more efficient than the Otto engine. The other thing, advantage actually, you don't really need spark plugs for this one because this whole the intake happens in here, and so you don't really need. You don't worry what do you call it, because when you compress the fuel and air mixture, when you compress them at high pressures, you might ignite and you might have a premature basically ignition before the engine, and that cause damage to the engine or knocks in the engine and all kinds of problems and mechanical problems in the cylinder. So you don't want the misfire basically in this case, and that's a problem. So, but in the case of and that's why you need spark plugs, and you have to be very careful not to take it too long in the case of the Otto engine. But for the case of the diesel engine, you don't worry about it because you really don't have fuel in there. So you can have a very big cylinder that compresses over a very long time, and that when it expands and give you a lot more work during the expansion stage to be more efficient in this sense, because you're not taking fuel during that time. So the diesel engine is a little bit better when it comes to efficiency. Okay, obviously the kind of fuel you can put in it also has another issue, and that's the air pollution and things like that. So in a sense, this is basically how engines are working. Do you guys understand, or at least have an idea of how this is working and how to compute things? Yes. Any one of you guys going to go to a mechanical engineering at all? Work with engines? No? Wake up, guys. I know it's early, but no? Okay, fair enough. Okay. I just want to pass physics 4C. I don't care about this stuff. That's acceptable too. That's fine too. Okay. Okay. So let's continue with this discussion about the most fascinating engine there is, and that is the Carnot engine. All of your problems and every single problem that you're going to be facing, you're going to be asked to compare the engine that you have before you versus a Carnot engine. Okay. Carnot engine is the most efficient engine. So that is basically the bottom line. So in this case, if we're going to compare this engine, where is it? To Carnot engine, I have to take the highest temperature possible. And the highest temperature possible is at point C, actually. This is the highest temperature. And compare it to the lowest temperature, which is point A. Okay. If I'm going to make this one into a Carnot cycle, those are the two temperatures I have to keep track with. Compare that with the Otto engine, you will find that the Carnot engine is more efficient. Take this one, actually, also the highest temperature, which happens in this point against C. Yeah, in this point C to the point A again, and you will compare the diesel engine to the Carnot engine, you'll find it's more efficient for the Carnot engine. So let's see how the Carnot engine, first of all, is. So again, we have a PV diagram. Doesn't matter where we start, because we're going to go clockwise too. So we have, in this case, an isothermal expansion. This is not an adiabatic, isothermal. Followed by an adiabat. So in this case, it's an adiabatic process. Then a compression at constant temperature. So this is an isothermal. And then we're going to compress further at through an adiabatic process, So the intake of heat happens here at the highest temperature. This is the same temperature to H because it's an isothermal. So the point A, point B, point C, and point D. So we're going in an isothermal this way too. I mean, we're going in a cycle this way too. So this is still clockwise, okay? The key thing in here is that this is, first of all, reversible engine. Okay. And every single stage in the process, you can go back. That's what the reversible means, okay? And that is the key for why this engine is the most efficient engine. And then you're going through an isothermal. That means constant temperature. You're operating only between two temperatures. And this is an isothermal too, sitting at T cold. So TH and T cold. There are no other temperatures in this engine. There are only two temperatures. This is going through an adiabat from point B to C. And this is a compression from D to back to A at also through an adiabat. There's no heat exchange. So Q is equal to 0 here. Q is equal to 0 here. And all the QH in here happens in this stage. And all the QC, the dumping of heat, happen in here because that's the only place where there is heat in there, okay? Again, we're going to find the same thing in here, the QH and the QC. We're going to find the work, and we're going to find the efficiency of this engine. So let's do that. Q hot, if you guys remember, because this is an adiabat, I mean an isothermal, the temperature doesn't change. That means delta U is equal to 0. And that is from A to B, by the way. The process from A to B is an isothermal process. Since the temperature doesn't change, that means there is no change in this case in the energy because the temperature is the same. Whatever heat you take from here, you're gonna do work with it. Okay, so there is no change in energy, and then that means that Q plus W is equal to 0, which means that Q is equal to minus W, and W, if you guys remember, we calculated to be minus, by itself, a minus nRT hot in this case, the ratio of the final volume, which is the volume at point B, VB, over the volume at point A. So I need to know these volumes too. So ln of VB over VA, okay? Minus times minus is going to be a positive. So it's going to be a positive value in here. So this is a QH. QH is going to be a positive value of nR T hot ln of the ratio of the volumes upon B over volume upon A. Okay, let me talk a little bit about this business of science again, okay? If we define it this way, we're going to get this value. If we follow the book and define the value of W to being exactly the integral of PDV, which is not convention, then the delta U in the book should be then is equal to Q minus W. Because this is 0 in this process, then Q is equal to W, and it's going to be the same value. Because when you integrate nRPV, remember PV equal to nRT, so T is constant during this process, so it's going to be nRT over V, so you'll integrate dV over V, so you're going to get an ln, and ln over final over initial, so you're going to get the same value in here as I have found it in there, so namely Q is equal to W. Which means that you take heat, and that heat is, again, dumped externally. But the way that the standard convention is, it's with the plus sign, and you take the minus into the definition of the work, and that's going to give you the same absolute value, the same value for the work, the heat, I'm sorry. It's going to be the same value. Algebraic and all, not just numerical, algebraic and all, okay? So the same sign, the same value. So this is Q hot. During the stage where we're going through the dumping heat, it's this point in here. We're going from VC, though, up to VD. So it's the same expression, except the final volume in here is less than the initial volume. So in this case, it's going to be the ln of VD over VC, and that's going to be a negative number because you're taking a ratio of a fractional number. So it's the same expression, and this is happening at different temperature, though, at TC. So during that stage, QC is going to be nR TC ln of the final, which is VD over VC. VD over VC. Okay? This is going to be a negative number, again, because this ratio is less than 1. VD is less than VC. Okay? So if we do the algebra and follow the algebra correctly, we're going to find this expression. Let's see here. So what we have found for the efficiency, again, it's the network divided by the QH. And the network is going to be just either the algebraic sum of the two divided by the QH, or just take this one with the absolute value. That means you flip the signs, okay? That's fine. So let's keep the algebraic expression. So this is QH plus QC, because we know QC is going to be negative, divided by QH. So this is going to be equal to 1 plus QC over QH. Again, it's going to be less than 1 because of the fact that this is actually ratio is less than 1 and it's a negative number. So the whole thing is going to be 1 minus something. Let's find it, okay? Obviously, I have QC and I have QH. All I have to do is take the ratio of the two. The NR cancels the NR, so it doesn't depend on the number of moles. And the R cancels the R, so I'll be left with TC over TH times the ratio of this ln's. So let's do that. So E is equal to 1 plus TC over TH. I already canceled NRs, okay, when I did this ratio of QC over T. So it's going to be ln of VD over VC divided by ln of VB over VA. Okay, these ratios, VB over VA. I'm going to show that this ratio is equal to a -1. Let's see how that's possible, okay? Again, I need to express VD in terms of either VB or VA. And I need to express VC also in terms of VB or VA. And if I do that, then I'm in business. So let's do that, okay? I know the point VC and the point C and the point D, they are part of the same, I'm sorry, the point C and the point B are the same adiabat. They're part of this thing in here. So in other words, this is the same deal that we were doing with earlier. So the point VC and the point VB are in such a way that VC times to the power gamma minus 1 times TC is equal to T hot times VB to the power gamma minus 1, okay? So that is one relationship. I also know that the point D and the point A are in the same also adiabat, different adiabat than the first one, but they're both on their own adiabat. So I know the point TC, the temperature at this point, times the volume in this point, which is VD to the power gamma minus 1, is equal to T hot, because that's the temperature for the entire isothermal, T hot times V, what is it? VA to the power gamma minus 1. So I need to combine these relationships. Let's bring them closer to one another and see how they look like. So the first point in here is that TC VC to the power gamma minus 1. TC VC to the power gamma minus 1 is equal to TB, which is T hot times VB to the power gamma minus 1. T hot times VB to the power gamma minus 1. So this is relationship number 1. If you guys are not following, please let me know, okay? I hope that you, if you have difficulty, you can come back to this one and pause it and go to basically according to your pace, and then also redo these calculations because it's very important. Actually, this is actually in the book. This is textbook example. So you will find this one in every single textbook, whether this one or higher or lower. So they go through the Carnot cycle. Okay, so again, we're going to do TC, the temperature at this point, which is the entire temperature in this entire stage, which is T cold. It's an isothermal, times the volume in this point, VD, is equal to 2 hot times VA, both of them to the power gamma. So we're using the same relationship again and again. So again, we're looking at the point D, which has the same temperature in here, is equal to T hot times VA to the power gamma minus 1, okay? If I take the ratio of these two expressions, the temperatures cancel. I'm going to take expression 1 over expression 2 because I need actually VD over VC, okay? And I need actually VB over VA. I have actually VB over VA from this side. So on the other side, I have the TH cancels, so a ratio of 1 over 2. The TH cancels, so I will have VB over VA to the power gamma minus 1. And I will have, in this case, VC over VD to the power gamma minus 1, okay? If I take the ln of both sides of this expression, the TC cancels, by the way, too, and the same thing like the TH in there. If I take the natural log on both sides, so what happened in this case, I will get a gamma minus 1 times the ln of VC over VD is equal to gamma minus 1 times ln of VB over VA. Again, this gamma is never equal to 1. It's always greater than 1, so I can cancel it. So I have ln of VC over VD is equal to ln of VB over VA. Almost there. I don't really, I have ln of VB over VA in the expression that I ended up with. This is ln of VD over VC, but I have ln of VB over VA. And here VB over VA under the ln, but I have ln of VC over VD instead of ln of VD over VC, as I should. So I really have to flip this sign. When I flip the sign, the ratio in here, I have to change the sign. So ln of VB over VA is equal to minus ln of VD over VC. This is the property of the natural log, okay? So all I did in here is just change the ratio and sign. This is the property of the natural log. Therefore, ln of VB over VA divided by ln of VD over VC is equal to -1. Exactly what I wanted to do, what I wanted to show. This ratio is actually equal to -1. So this whole thing, the efficiency of the Carnot engine then, E, is going to be 1 minus TC over TH. This is one of the most important results that you need to remember from this chapter. Probably the most important one. This is the efficiency of the Carnot engine. Carnot cycle. So why in the world is it the most efficient engine? So this is its efficiency. So when I was talking earlier about the Otto engine, what is it? Way back up. If I want to compare it to a Carnot cycle, this is the efficiency of the Carnot of the Otto engine as compared to 1 minus this temperature at point A divided by this temperature at point C. These temperatures must be in Kelvin, okay? They cannot be in centigrade or any other unit, okay? So if I want to compare this value to that value, I will always find that this value is less than the ratio of 1 minus the ratio of this temperature versus that temperature. The same thing. There is another formula. I didn't do the calculation, but it involves actually the value of beta and R also. And that I need to compare it to the ratio of this temperature versus that temperature, 1 minus that ratio, and that would be how I compare it to a Carnot engine. So if this were a Carnot engine, and it's not, it's a diesel engine, its efficiency would have been 1 minus TA over TC. This is the A, and this is the C. This is the lowest point, and this is the highest point. Both of them are in Kelvin, by the way, not in any other unit. Okay, number one. And number two, this is actually an upper limit. So if somebody does a calculation for you and does an engine, it doesn't matter what that engine, and it's not a Carnot engine, and they come up with an efficiency more than a Carnot engine, you know that they made a mistake. You know that's a rejected thing. It cannot. It's just like somebody calculating the speed, and all of a sudden the speed is greater than the speed of light. You know that's nonsense, okay? 3 times the speed of light, you know that they made a mistake somewhere, or they used the wrong physics somewhere, or they have a problem somewhere that they need to address. Same thing with this thing in here. So this is the upper limit on this engine, okay? So it's on any engine, it's this one. So this is what I'm trying to show right now, is that this is an upper limit. No engine can be more efficient than Carnot engine. So let's see why. Here is the deal. Let's say, for example, Mr. Carnot engine operates between 2 temperatures, TH and T cold, okay? And for some reason, in this example, we're taking 100 joules from this engine, from this process, and we're only getting 20 joules out of it. So we know that we're dumping 80 joules in form of heat. So this is Carnot. And you came and you claim that, listen, I came up with an engine that is better than this one, okay? So this is the claim. This is my claim, okay? That, listen, I take the same 100 joules that obviously the efficiency of this engine, E, is the ratio of the work over the heat, okay? Remember, it's W over QH. And in this case, it's going to be 20%. That's why I took simple numbers so that I can do the math. It's 20% efficiency. So I claim that I can have 40 joules out of a different engine. It doesn't matter which design that is, okay? This engine, I have worked very hard on it, and I made it so that I can only get 60 joules dumped into the cold source, and I get 40. Obviously, this engine has a 40% efficiency. Okay, this is my claim. I'm going to prove that this is not correct, that this is not true, if the second law of thermodynamics is to be observed. Okay, so let's see what we're going to do, okay? We're going to do the following. We're going to take a Carnot engine, because it's reversible. We're going to reverse it, actually, okay? We're going to actually take 2 of it first. Since we can make one engine operating at 20% efficiency, all I have to do is make another one operating at 20% efficiency. So 2 times Carnot engine, twice Carnot engine, will do the same thing. 2 of them will take instead 200 joules of energy, get that 40 joules of work because it's still operating at 20% efficiency, and dump, of course, the excess, which is 160 joules to the T cold source. So this is 2 times Carnot engine. Of course, you see why I cooked the numbers so that they do this way. Okay? They work this way. Okay. Then, because this is reversible, I'm going to reverse this one and make it into an AC unit, basically, into a refrigerator. So I'm going to reverse it. So instead, I'm going to take the 40 joules and extract 160 joules from this source and dump the sum to the hot source, which is 200 joules. So this is reversed now. It's working as an AC unit, okay? And connect it with my claimed more efficient engine and the same temperatures. So my claimed one will give me 40 joules, will take 100 joules and dump 60 joules. Take both of them and now connect them together in a block box so that nobody can see what's inside, okay? So this is the net thing if I connect the 2. Obviously, the 40 joules I take from the claimed engine, okay? I'm going to use it in this refrigerator so that to pump the 160 joules from the cold source to the hot source, okay, and dump the sum, which is in this case 200 joules in there. So this is how it looks like from outside when the 2 are connected. It looks like I'm dumping 60 joules to the cold source, but I'm taking 100 joules off of it. So I'm taking 100 joules from here, from the cold source. Okay. This is an internal operation. It cancels. I'm taking 40 and using it immediately. So this is cancels. So it's not going to be shown for the external user. And in here, I'm taking 100 joules from my claimed engine, from the hot source, but I'm dumping 200 joules to the cold source, to the hot source, I'm sorry. So I'm taking 100, but dumping 200. So there is a net dump in here of 100 joules for the hot source. So for an external, it looks like I have found a way to beat the second law of thermodynamics, because this is a process that looks like it's completely unsupported. There is no input of energy from outside whatsoever. It's only contained in this black box where I take energy at will from a cold source and make it colder and make the hot hotter, which is impossible. This violates the second law of thermodynamics. Therefore, because this is impossible, Because I can always, I mean, the Carnot cycle was led to this efficiency, and it's reversible, and it can make two of it. So everything up to here with the Carnot cycle is correct. So the only thing that is wrong is my claim is incorrect. So in order to still comply with the second law of thermodynamics, I cannot have an efficiency as I said of 40%. So I must have made a mistake somewhere, or this is not possible. Impossible. Obviously, I cooked the number so that this example works a little, but it doesn't matter how small it is. You can always take a fraction of the Carnot engine and add it to the Carnot engine and reverse it because it's reversible, and add it to your engine. And now you have a closed process that is completely unsupported, where it's completely basically by itself, supporting itself, somehow extracting heat from the cold source and dumping the excess heat in the hot source, and that violates the second law of thermodynamics. So that's why Carnot engine is the one that has the most efficiency. Otherwise, the second law is violated. It's fun, isn't it? I mean, it's really amazing how this guy in the early 1800s came up with an idea that nobody could beat. That is similar to the idea of the speed of light in a sense, okay? So this is the most efficient engine there is, okay? We still have one more concept, and then we're done with this chapter, and the concept of entropy. And the concept of entropy is also another conserved quantity during a cycle. It doesn't matter which cycle that is. So I'm going to take the Carnot engine actually as an example. When we went from this process, from point A to point B, in this case, the temperature was constant, okay? The heat was taken at QH. The heat was taken at this rate. So I'm going to follow this quantity. Let me tell you what that quantity is. By definition, through every infinitesimal step, an amount of heat dq is added, parentheses removed, it doesn't matter, okay? Okay, so this is an algebraic operation. We define a change in entropy ds equals to dq over t, okay? Where T is temperature in Kelvin and dq is the amount of heat added. So if we follow this quantity, we'll find that it's going to be also unchanged, because through a cycle like this one, any cycle, it doesn't matter. We talked about that last time. The temperature doesn't change if you come back to the same starting point. The volume does not change if you come back to the same starting point. The pressure doesn't change if you go through and come back to the same starting point. The energy does not start if you come back to the same point. I'm going to show that this quantity S also does not change if you go and come back through the same starting point. So this is also going to be a state variable. So far we will have 5 state variables. Q and H, they do depend on the area. They do depend on the cycle. So they are not state variables, okay? The work and heat are not. But their sum is, actually, their sum is the energy, which is the total energy of the system, which is going to be a state variable. So S also would turn out to be defined this way, to be actually a state variable. So let's look at it for the Carnot cycle. Carnot cycle. When we went from A to B, this was an isothermal process. So in this case, for this case, dq is equal to minus dw. Because remember, du is equal to 0 on an isothermal in every given stage in here. Always, there is no change in temperature, there is no change in u. So that means that dq plus du is equal to 0, and that's exactly how much dq is. Remember, dq then is equal to minus times the minus, so it's going to be plus p dv. And this regardless of which definition you use, whether you use the definition, the standard definition where the work is equal to minus PdV, or you use the definition that is in the book, which is PdV. So it's going to be the same because they use in here plus. They use a minus in here, and we move to the other side, it's going to be plus. So dq in the isothermal is going to be this way. And PdV is equal to PV in this case, always equal to nRT. So in this case, P itself is going to be nRT over V. So if I sub in that expression, dq is going to be simply equal to nRT over V dV, which brings me to the expression that I just defined for ds. All I have to do is just divide it by t. So that gives me ds equals to nr dv over v. When I integrate this expression, it's going to be just the integral from vb to va. So it's going to be just vb over va, which is just a natural log. So it's going to be s. The change in entropy in this case is going to be nr ln of the final value, which is vb over va, which is exactly the same quantity as q in this case, which is nRT times the ratio of the volumes. Where is q hot? That we wrote up there. Okay, it's this expression divided by T hot because the temperature is at T hot. Temperature doesn't change. So this is fine. VB over VA times NR, and this is the amount of entropy change in this case, okay? Now, so this is going from A to B on this isothermal A to B. Now, on the point from B to C, dq, this is actually an adiabatic process. Adiabat. In this case, dq is equal to 0 because it's an adiabatic process, which means that immediately ds is equal to 0. There is no change in entropy in an adiabatic process. That's why sometimes the adiabatic process is also called an isentropic process. A process that does not change entropy, because we cannot say change of heat. Heat is not a state variable where you're concerned about its change. There's an exchange of heat or work done and done against, but you cannot say change in work or change in heat. Doesn't make sense, completely nonsense. But you can always say change in variable because I'm going to show that it's also state variable. So now this is a process where the entropy does not change. So an adiabatic process sometimes is referred to as an isentropic process because the entropy doesn't change on it because there is no heat exchange, and this is proportional to the heat. So in this case, there is no heat exchange, there is no change in entropy, okay? So in this case, that is from B to C, so delta S is equal to 0. So when I go back to this process and keep tab of what's happening to the entropy went up in the first case, okay? Because the ratio in here is positive, VB over VA is positive. So this ratio was increased. In this case in here, the entropy does not change. In this case, the entropy will go down because the temperature, the volume at D is less than volume at VC. As a matter of fact, the expression is going to be identical with the expression of TC is going to be canceled because we're going to integrate the same expression from initial volume to final volume, which is from VC to VD. But then the temperature we're going to divide by it, so it's going to cancel. So again, from C to D, which is another isothermal process, from C to D, isothermal process, it's the same repeat of the calculation, and change of entropy in this case going from C to D is going to be NR. And again, the temperature drops because we have it in the denominator and the numerator, times the ratio of the final volume, which is in this case VD over VC, okay? This number is clearly negative because of the fact that the ratio of the ln's, where is it? VD over VC is less than 1. So the VD over VC is less than 1. So that means the ln is negative. As a matter of fact, we found the ratio of the ln's in terms of the previous ones. Okay. We showed that VD ln, as shown when we were calculating the efficiency, ln of VD over VC is equal to minus ln of VB over VA. And this is positive number because VB is greater than VA. So this is actually equal to delta S from C to D is equal to minus NR ln of VB over VA. And VB over VA times NR, that is actually the entropy from A to B. That is actually equal to minus the change in entropy from A to B. With the exception, if the first one was positive, this is exactly negative, and it's equal to it. Okay. The final stage from D to A in this cycle, that's also an adiabat. That too, there is no change in entropy. That too is an isotope because there is no change in heat. There is no change in entropy in that stage, and that is from D to A. So if I want to keep track of the entropy going from A back to A, by going first from A to B, plus going from B to C, plus going from C to D, plus going from delta S. From D to A, well, it's going to be 0. Let's see why. This one turned out to be NR, ln of VB over VA, NR, N times R, ln of VB over VA. This is 0. This will turn out to be exactly negative of that number, and we saw why that is. It's actually VD over VC, and VD over VC is actually equal to minus ln of VB over VA, and this is 0. Obviously, when you add them up, it's 0. So this is state variable. When you go through a complete cycle, it doesn't matter really which cycle there is, the entropy does not change, at least in this ideal gas that where the process is where the process is reversible. Okay, so when the process is when the process is all the processes are reversible. Okay, delta S is equal to 0 in a cycle. Okay. In general, though, processes are not reversible. That is an ideal situation. So any process cannot be reversible. Therefore, actually, the entropy cannot be equal to 0. In general, the entropy, the change in the entropy is more than, in general, the change in the entropy is more than 0. In the ideal situation is equal to 0. Okay. So this is actually a restatement of the second law. This is another way of expressing the second law. Okay, so in a closed system, the entropy does not decrease. I mean, it could stay 0, it could increase. That's what that word means. So this is in another way, this is basically the point that I want you guys to put it as an alternative in the discussion here for the second law. The entropy in a closed system, the entropy of the universe, because it's a closed system, does not decrease. The entropy of the universe does not decrease. There is a minor issue in here that we can talk about quickly, is that the entropy and the order are related to one another because of the fact of this ratio of volumes. As the gas expands, there is more possibility now for states to exist in different formats. And this involves actually statistical mechanics, but the point in here is that entropy is actually a measure of entropy is a measure of the different ways to organize substates, which usually are quantum states to macroscopic observables. Okay. This requires a little bit of something that is outside of the scope of this class and requires basically statistical mechanics. If we do it this way, mechanics. If we do it this way, we can define the change in the entropy as actually equal to Boltzmann. That's what Boltzmann actually has shown. Boltzmann constant times the natural log of a quantity, in this case, which he called it omega, which is a measure of how many ways you can organize basically a variable in here, in this case, okay? An observable, which is basically the macro state of the system in terms of its micro states, okay? And it involves both statistical mechanics. It involves a branch of mathematics called combinatory. I mean, I usually have a hard time saying the word, but I can write it down for you guys. In French, they call it l'analyse combinatoire, which is, I think they call it tricks or something like that, okay? Combinatory analysis, if you want to translate the words, okay? But it requires basically how many ways. It's like playing basically dice and probability and things like that, because it's statistical observations. Outside of the scope of this, the key thing in here is this definition is critical in terms of your exam, in terms of your lab, in terms of everything else. Where is it? This one in here. dq is equal to ds. So this calculated. Now we calculated for the isothermal process. Because for the isothermal process, it's this value, nr times the ratio of the logs, the final over initial. So we know how much it is. So let's summarize this one, and that's going to be the basically the last of this chapter. So the different processes, entropy calculations. Okay. In an isothermal process, we did that. For an isothermal process, the change in entropy in this case is going to be nr times the ln. So it doesn't involve the temperature in this case, of V final over V initial, okay? In the case of an adiabatic process, that is actually the easiest. In the case of the adiabatic process, then in this case, delta S is equal to 0. In the case of an isochoric process, well, in this case, dq is equal to ncv dt. And then if I write the expression for the delta S as the sum of dq over t, then in this case, I have ncv as a common factor times the integral of dt over t, and the integral of dt over t, that is just going to be an ln. So the delta S in this case is going to be ncv ln of t final over t initial. These t's are in Kelvin. Okay, not in anything else. Okay, in an isobaric process, it's going to be identical. Isobaric. Well, then in this case, dq is equal to ncp dt. So the only thing that we're going to trade off in here is cv by change cv to cp. So it's going to be the same thing. Delta S is going to be ncp ln of t final over t initial. Okay. Sometimes it's written in terms of gamma, but don't let that fool you, because Cp and Cv are related to one another through the relationships that we found. Cp over Cv is gamma. And don't forget that Cp is equal to Cv plus R. And that gives you also how Cp and Cv are related to gamma too. So those are the two main relationships that you need to keep tab of. Okay. And the fact that Cp over Cv, which is equal to 1.4 for the diatomic gas, and depending on a lot of the calculations that we're going to be doing for the engines are going to involve diatomic gases, okay? Because that's the air, basically. You take usually hydrocarbon, which is some complicated chemical, what you call it, organic chemistry molecule, combine it with the air, and the air is the main component in it. So it's going to be mainly 1.4, okay? Which is basically nitrogen and hydrogen and oxygen. Nitrogen and oxygen are both diatomic gases. So that's why gamma for most practical problems is going to be that of the 1.4. Okay, so CV would correspondingly then, because CV and gamma are related, if I divide in here by CV, it's going to be gamma 1 plus R over CV. So this can give me a value for R using the value of, CV using the known values for gamma and R, okay? And then we can go and find what CP is, which is just gamma times this number, okay? Anyway, so gamma times CV, I'm sorry, when we solve for this equation. Anyway, so let's, we still we did the isobaric, the isochoric, and the adiabatic and the isothermal. There is another process that you're going to be involved with a lot, especially in terms of homework and in terms of exams, and that is the case of calorimetry. The change in entropy there, because during that time, dq is actually equal to mc dt, where m is the mass of the object times c, which is the specific heat in that case, times dt. This is actually, there is another one that involves the molar values. So instead of using m, we use n, the number of moles, but that requires a different definition for the specific heat in that case. But both of them are going to be similar when it comes to the entropy. So the delta S in this case is going to be, it's going to involve the same thing. It's going to be mc times dt over t. M and c are constant, so they come out of the integral. And this is going to be, again, ln of t final over t initial. So these are the places where most of the time are going to be dealing with the entropy change and how you calculate it and things like that for different processes. Because this is a new quantity we just introduced, so we need to know how to find it. A big word of caution, and I have seen it in exams actually several times, and please do not make that mistake. If the process is isothermal, like, for example, if I take my coffee and I want to warm it, okay? So what I do in this case, I take a resistor and plunge it in it, okay? Connect it to electricity. Those are usually isolated. So it's going to heat up, and during that stage, it's connected to the power plug, okay? During this entire stage, this one is sitting at some temperature. Let's say, for example, at 150 degrees Celsius. Okay, I have to be careful in here. So for this metal, it's going at constant temperature. So this process, because you have it plugged, you wait for it to warm, and then you plunge it into the coffee or whatever, the water that you want to heat. And now you have an amount of water that was sitting at 0 degrees Celsius, let's say 20 degrees Celsius. It is sitting at room temperature, and you want to warm it up to, let's say, for example, to 70 degrees Celsius, okay? So this is 70 degrees Celsius. So of course, you know how much heat you're going to get out of it in this case. But then you want to find the change in entropy in this case. So if you want to find the change in entropy, you have to use this formula. But make sure you convert TI from 20, add to it 273 to do the calculation. And make sure that you add 273 to 70 to do the calculation. So in this case, I'm going to find how much entropy has increased in the water, correct? Has increased in the water. Let's say, for example, for the case of argument, we took 1 kilogram, 1 liter of water. Okay, so we have 1 kilogram of water. And we know the specific heat of water is 4,190 joules. So if we do this calculation, how much time? We still have about 5 minutes. Okay, so delta S in this case, in this particular example, will be equal to that of MC, which is 1 kilogram, times 4,190 joules, that is per kilogram, that is C, times ln of 70 plus 273 divided by 20 plus 273. I'm not going to do the calculation, but I'm assuming that you can finish this calculation. So you know how much entropy went up. Now you're asked how much entropy did that of the resistor go, the one that was used to warm your coffee. Don't think for a moment, because it's an isothermal process, and they tell you it's an isothermal process because it's connected to the power plug. So its temperature stays fixed at 150 degrees Celsius. Okay, so don't think because it's an isothermal process, there is no change in entropy. As a matter of fact, there is, because it's lost this much heat. What is the heat that it lost? It lost delta Q, which is equal to, or Q, there is no such a thing of delta Q. Q lost in this case is going to be the one that is taken by the fluid in warming it from 20 to 70 degrees. And that is, again, 1 kilogram times 4,190 times the change in temperature from 70 to 20. That is 50. So this is how many joules actually went to heat the water. And that energy came from somewhere. It came from actually the resistor in this case. So the resistor has a change in entropy in this case of delta S equals to, this is the water. This is the resistor that was used to heat this element. And in that case, it's this Q divided by the temperature. And its temperature is 150 degrees Celsius. So it's 150 plus 273. Okay, so that is how you find the entropy in this case for that particular example. I think this is one of the examples that probably we're going to be doing. And I want you guys to understand the key concept in here that some of my students make. And during exam time and their stress, they see it's an isothermal process and they think that because dq, they have been already exposed to it, involves dt in here, since there is no change in t, they would be tempted to think that in this case, hey, obviously there is dt is 0, so dq is 0, therefore I don't have any change. No, that resistor lost heat, therefore its entropy actually went down. Obviously you're going to compare the two. This going down is going to be a negative number, by the way, because it's going to be minus that one, because that's what the one that heat the water, so it's going to be minus this quantity divided by that number, and you add it to this entropy, and you will find the overall entropy of the universe as caused by this process when you want to warm your coffee. And in doing so, you should see that the entropy should go up per the second law of thermodynamics. Okay? I think we're going to have enough examples in here. Please join me. I know still have about 2 minutes. Join me this afternoon for the lab. We're going to have fun discussing it. It's going to be long calculations, but that's typical of what we do in here. And hopefully you guys enjoying working and doing stuff. And if you have difficulty with any of these calculations or things like that, please let me know. We have finished, we did chapter 12, 15, 16, 17, 18, 19, and 20. So we did 7, how many? I lost track, 7 chapters of this book. We still have quite a few. We still have 4 more chapters, and basically we're done. 12, 15, 16, 17, 18, 19, and 20, yes, okay? So this is the first midterm, which is really a big deal in terms of that. In terms of problems, you need to focus on these problems of the engines. You will definitely have some, and you'll be calculating the entropy for the exam, and also you will have problems from, I would say, waves, okay, especially with the Doppler effect and things that are related to beats and things of this nature from the previous stuff. Okay, so let me stop sharing the screen. And I'll see you guys in this afternoon at 2 o'clock. Good. Yes. Okay, some of you left. Thank you.